So last we met, we started talking, we were talking about the equilibrium constant. Well, we didn't. We're just about to start talking about the equilibrium constant and how it relates to the free energy. Okay, so just to refamiliarize, we know what the reaction quotient is. The reaction quotient is determined from the non-equilibrium concentrations, right? So the initial concentrations of the reactants and products. So here's just a generic reaction. We have A and B reactants going to C and D products. And in the reaction quotient, it looks just like the equilibrium constant. Again, no solids or liquids would actually appear. So it's going to be the concentration of the products, each raised to the coefficient in the balanced chemical equation, divided by the concentration of the reactants, again, each raised to the coefficient in the balanced chemical equation. But again, these are the initial concentrations, not the equilibrium concentrations like K, the value of K. So when we want to compare, we always compare Q to K, right? So if Q is less than K, that means I don't have enough products. Because again, it's got to equal K. If I don't have enough products, the reaction is going to proceed to the right towards more products. And if K is greater, or Q is greater than K, that means I have too many products, and the reaction is going to shift back towards the reactants. And of course, when Q is equal to K, we are at equilibrium. Okay. Okay, so now the free energy changes with reactions at non-standard states. In other words, something other than 1 atmosphere or 1 molar. Well, we could use this equation here then to determine what's going to happen to the reaction. Okay, so basically, we're going to plug in our value for Q. We got to figure out what our standard free energy is. You could do that generally from just using the tables for the free energies of formation, okay, and calculate that standard free energy change, or sometimes there's other ways to calculate that. So whatever you need to do to calculate the free energy change. And then whatever this value is, if this value is negative, do you think it's going to proceed to the reactants or products? If this value is negative. Well, if it's negative, it's spontaneous, and that means it's going to go to the products. But if it's positive, in chemistry, what that means is that it's going to proceed back towards the reactants. So spontaneous, it proceeds to the products. Non-spontaneous, it goes back to reactants. Unless, of course, it's already at equilibrium, then del G is going to equal to 0. So this will simply equal to 0 if it's at equilibrium. Okay. Okay, so let's look at it. So again, at equilibrium, del G, so this isn't the standard, but del G would be equal to 0. So if this is equal to 0, I can then say that Q is equal to K, right? At equilibrium, Q is equal to K. So now I have an equation that relates the free energy to the equilibrium constant. So just rearranging it, subtracting this from both sides, I get that the standard free energy change is equal to negative RT, the ln of K. And again, this R is at 8.3145 joules per Kelvin per mole. Okay, so now I have a relationship between the free energy change and the equilibrium constant. So again, when K is greater than 1, the ln is going to be positive, and so del G is going to be negative. That'll give us a spontaneous chemical reaction. If K is less than 1, then the ln is going to be negative. Negative times negative is positive, and therefore del G is going to represent a non-spontaneous reaction. So now you can see this relationship between spontaneous and the equilibrium. If K is greater than 1, we have a spontaneous reaction. It proceeds, you have more products than reactants at equilibrium. For a non-spontaneous reaction, with K less than 1, you have more reactants than products. Again, it doesn't mean that any products are not going to form. They will until it reaches equilibrium. But the reactants are going to be favored. When it's non-spontaneous, the reactants are going to be favored at equilibrium. And for a spontaneous reaction, the products are going to be favored at equilibrium. We can look at this graphically like this. So this is going to be the free energy of the reactants. They were here. Here's the free energy of the products. They are here. So we can see that at equilibrium, the difference between these two values is negative, right? It's a negative value. So that tells me that this reaction has a negative del G, which means the products, so these are products, at equilibrium, we can see that the products are favored over the reactants. Now, there's still some reactants left, but it's mainly products. Okay? So when Q is less than K, that means the reaction is spontaneous and it's going to continue to proceed until equilibrium is reached. If Q is greater than K, that means I have too many products. And again, it'll be spontaneous in this direction till equilibrium is reached. And of course, it would be non-spontaneous to try to go back this way and non-spontaneous to try to go back this way. Now, again, we can force it to go in these directions, but we would have to add energy to the system to make that occur. Okay, does anybody have any questions about that? Okay, let's try an example. So let's find the value of the equilibrium constant, Ka2, at 25 degrees Celsius for aqueous hydrogen carbonate. So that's the hydrogen carbonate dissociating to form the hydrogen ion and the carbonate ion. Okay, so we're going to use the standard free energies to do it. So the standard free energy, what I would do is I would use the summation law. I would look up the standard free energies of the hydrogen ion, which are actually 0, the carbonate, which is a non-zero number, and the hydrogen carbonate, which is a non-zero number. Take this value minus this value, and that's going to give me a free energy change then of 59 kilojoules. Now I'm going to turn it into joules because we want to use that equation where R is the molar gas constant, which is in joules per Kelvin per mole. So that's why I switched it here to joules, but that is the free energy change. Does everybody understand how I got that value?
I have a quick question. Would it be the same thing if you converted the R value to kilojoules instead?
Oh, absolutely. Yeah, as long as your units are consistent. Let me think about that. Yeah, I don't see why. The only bad thing is it puts your, no, there's nothing wrong with that. Perfectly fine. Okay, so now del G then is going to be our 59 kilojoules. So there is our balanced thermochemical equation. So the ln of K then is the change in free energy divided by negative RT. I'll plug in my values. Okay, so the moles cancel, the joules cancel, the kelvins cancel. So that gives me a unitless number. That's a good thing. So that's negative 23.8. Now I want to take the anti-log of the natural log. So this is log base E. So it's going to be E raised to the negative 23.8, which means K is 4.6 times 10 to the negative 11. So is my products or my reactants going to be favored in this case?
Reactants?
Yeah, right. I mean, this thing is really, really tiny. So very little of it actually dissociates into that. So this is the Ka2. So this is the Ka2, and experimentally, it's determined to be 5.6 times 10 to the negative 11. So again, using the free energies of formation, and since these things are all state functions, you can see that we can get a very, very close to an accurate value by simply using the free energies of formation and comparing them to the equilibrium constants. Now, how are these original free energies of formation found? Well, they're found in a whole bunch of different ways. We could have looked at the equilibrium constant of this, right? And work backward from the equilibrium constant to del G. And they do that, except that they do it for a whole bunch of different types of chemical reactions and then basically just take the average. Okay? So that's how they're finding these values. They're slightly different for whatever experimental reasons. I mean, realistically, they would be exact. But because of our experimental error, there's always going to be some small amount of error within the values that we calculate. Okay, any questions about that?
I have a question.
Yep.
Change of free energy value. Could you also have calculated for del H and del S and then solve for that value?
You could have, but why would you do that?
I don't know. I just wanted to like ask.
That would take almost 3 times as long. Since this is already at 25 degrees Celsius, why not just use the free energies of formation? You could have. Your value might have been slightly different than this. Canvas would have marked it wrong. On your exam, I would have given you credit for it as long as the math was correct. But again, you just wasted a lot of time doing it that way. The only time you use del G is equal to del H minus T del S, 2 circumstances. One, you have non-standard conditions. In other words, your temperature is not 25 degrees Celsius. Or like the problem that we just did, where we were looking for the temperature at which the reaction goes from spontaneous to non-spontaneous. Otherwise, if you are at 25 degrees Celsius, make sure you're using the free energies of formation to calculate the standard free energy change. Okay, again, you just don't want to waste time. That is it for this chapter. I do want to do a couple of problems. Yet is the relationship between the free energy and the equilibrium constant. So we're going to find out that the change in free energy is equal to negative RT, the ln of K. In this case, the R value, what do you think the R value is for this? Jada, what do you think the R value is for this equation?
The R value is 0.0820.
I'm sorry, give me 1 second, I can't hear you. Go ahead, say that again.
0.
0?
0.08.
Oh, 0.082058.
Mhm.
Everybody agree? Anybody disagree? What units do we expect?
Isn't it the kJ?
Kilojoules, right? Right? So the free energy has kilojoules, but the 0.082058 is atmosphere liter per Kelvin per mole. So the R value that you're going to need,
8.13.
yeah, 8.3145 joules per Kelvin per mole. Okay. Now again, remember this is in joules, and the free energy is generally given in kilojoules. So there's going to be a conversion there. So be careful with that. And this, of course, is the absolute temperature, which again is dictated by the variables in R, the molar gas constant. Then we're actually going to be able to predict which way a direction can proceed from the free energy itself. We're going to say the free energy in relationship to the standard free energy plus RT, the ln of Q, that reaction quotient. So here's that reaction quotient again. So this is going to be able to tell us which way a reaction is going to go. All we have to do is calculate the standard del G and then use the initial values, the initial concentrations in the chemical reaction, find Q. And again, we're going to see that if del G is negative, it's going to proceed in the forward direction, right? Because it's going to be spontaneous, and we associate spontaneous with going into the forward direction. And if del G is positive, that means we have too many products. It's going to be non-spontaneous. And in chemistry, what non-spontaneous means is that it's going to go from products to reactants if it's not at equilibrium. And if it's at equilibrium, what do you think del G is going to be? Well, del G is going to be 0, right? If negative is spontaneous and positive is non-spontaneous, well, 0 must be equilibrium, which again is spontaneous, but we'll refer to it as equilibrium. Now, there are a whole bunch of ways to express G. I mean, right here, we see 3 different ways, right? I can write del G. I can write del G naught. I can write del G naught F. I can write del G naught T. And I can even write del G M. Each one of these means something very different. So this is the standard free energy change, right? So that means it's at 25 degrees Celsius, 1 atmosphere, 1 molar if we're talking about solutions. This was the standard free energy change, which I'm just going to go like this of formation. So in other words, this is the free energy that would be generated or consumed for the formation of 1 mole of whatever chemical you're talking about from the elements in their standard state. Then this one here we just talked about, right? That's the standard free energy change for a non-standard temperature. This is just a molar free energy change. So molar free energy change. That's going to have units of kilojoules per mole. As we've seen, this is just going to have units of kilojoules. The entropies of formation are given in kilojoules per mole in the table, but if it's part of a balanced anytime these values are part of a balanced thermochemical equation, their units are only ever going to be kilojoules. And then we have the standard free energy change again, which is just going to be in kilojoules. And again, sometimes these things can be in kilojoules or kilojoules per mole, and it really depends on how you're using them. Now this one here, this is the standard free energy change of the reaction at whatever pressure or temperature, it doesn't matter. That's the actual free energy change of that reaction. Okay, this is something that we would most likely measure in the lab. Okay, any questions about any of that good stuff? It says carbon monoxide and hydrogen. So I have carbon monoxide and hydrogen gas favor the formation of methane under the right conditions. Okay, so if the initial concentration of reactants and products in a reaction vessel are 3 molar carbon monoxide, 0.35 molar hydrogen, and 0.1 molar methane and 0.15 molar H2O maintained at 1025 degrees Celsius, determine if this reaction will produce more methane using the thermodynamic values. So what equation would we need to solve this?
Q, the quotient equation.
Okay, but that only works if we know K. Do we know K?
No. Can we
find
look
K?
it up? Yeah.
We could find K. How?
Products over reactants.
No, that's Q, right? We can find Q because Q is just going to be, actually, I'm going to write that here. So Q is just going to be the concentration of the products, each raised to the coefficient in the balanced chemical equation. In this case, they're ones, but Q is the initial concentration divided by the products. Again, each raised to the coefficient, but again, these are the initial. And they gave us the initial concentrations, right? So they already gave us them. So the methane was what? Was 0.1 molar. I'm going to ignore the units now, right? Because Q and K don't use their units. The H2O was at 0.15 molar. The carbon monoxide was at 0.3. And the hydrogen was at 0.35. Okay. And that, of course, is cubed. Don't forget that part. And you would plug that into your calculator. And okay, I got these switched, but okay, so I'd plug that into my calculator and I will get 1.166. Okay, but now how do I get K?
Do you look it up in the
There's no K values for this kind of reaction, right? You can look up K values for acids and bases, but there's no acids or bases here. You could look it up for a solubility product, but there's no precipitation going here. You could look it up for the formation of a complex ion, but there's no complex ions going here. So that's not going to happen. We can't look up K this time.
can you do delta free energy equals negative R constant times temperature times ln of K?
Absolutely, right? Whoops, we'll just make that a K. I could absolutely do it this way, right? But I would need to rearrange for K, so I would divide both sides by negative RT and then take the anti-log. So after you would rearrange it, it would look like this. We know R, that's the 8.314. We know the temperature. Now that would have to be converted to Kelvin. And then how would I get del G?
In the tables of chemical data.
Yeah, right. So we have this reaction. CO gas plus 3H2 gas in equilibrium with CH4 gas and H2O gas. Now, what am I going to look up exactly? What equation do I need to use? So I'm looking for del G.
Since it's not at standard temperature, would you have to use delta G T equals delta H minus T times delta S?
Absolutely. Remember, you can only use the free energies of formations if it's at 25 degrees Celsius. It's not. So we're going to have to look up, we're going to have to figure out what del G of T is, which of course is del H at standard conditions minus T del S at standard conditions. So we're going to have to figure out what del H and del S is. So we're going to have to look up those values first. And so you're just going to look them up. So I will look them up. So for carbon monoxide, it is negative 110.5 kilojoules per mole for the enthalpy of formation. And for the standard entropy, it's 197.7 joules per Kelvin per mole. And then you're just going to simply look up the other values for each of your reactants and products. Now we could plug into the summation laws. And so that'll be our products. So our 1 mole of methane at negative 74.6 kilojoules per mole. then plus our 1 mole of water at negative 241.8 kilojoules per mole. We'll subtract from that our reactants, so the 1 mole of carbon monoxide at negative 110.5 kilojoules per mole. And we'll add to that our 3 moles of hydrogen, but that's at 0. So really we didn't even need to do that one. That one's just going to cancel. All of our moles are going to cancel out. Plug that into your calculator, and you're going to get a value of negative 205.9 kilojoules. Okay. So it's going to be 1 passed, right? Because this is 1, 1, 1. So it's just going to be 1 passed, 1 passed, 1 passed. We're going to do the same thing for del S. So the 1 mole of methane at 186.3 joules per Kelvin per mole, plus the 1 mole of water at 188.8 joules per Kelvin per mole. And we'll subtract from that the 1 mole of CO at 197.7 joules per Kelvin per mole. And the 3 moles of the hydrogen at 130.7 joules per Kelvin per mole. So now again, all of the moles cancel. It's going to leave us with joules per Kelvin. Plug that into your calculator. That's going to be negative 214.7 joules per Kelvin. Again, I'm going to need to convert that. So I'm going to immediately divide it by 1,000 because I know this is in kilojoules. So I'm just going to make that in kilojoules. So our joules would cancel. And that would give me negative 0.2147 kilojoules per Kelvin. Okay, so that's just what we've always done. Now I can calculate del G of T, which is going to be negative 205.9 kilojoules. And I'll be honest, in this case, we probably should have converted both of these to joules. I'm actually just adding an extra step by doing that. If we think ahead, we know that we're going to need joules because of that R value. Okay, so then we're going to subtract from that, our T value, which is 1,025 degrees Celsius, but we got to add 273.15 to that to put it in Kelvin. And then our S value, which is negative 0.2147 kilojoules per Kelvin. So our Kelvin is going to cancel. Then we have kilojoules, in this case, plus kilojoules. So your del G value then, your del G of T value then is 72.812 kilojoules. But again, I need to multiply that by 1,000 because I need it in units of joules for the next step. So the kilojoules are gone. So that means this is going to be 72.812 times 10 to the third. I know it's not proper scientific notation, but this is just an intermediate value. And the only time we need to show proper scientific notation is when we report our final answer. Okay, so now we could actually calculate K because now we got our G of T, okay? And I'll do that real quick, but then I'm going to show you another way we could have done this. So this then was going to be equal to E to the negative, this quantity, 72.812 times 10 to the third joules over 8.3145 joules per Kelvin per mole. And then our temperature which is going to be, so it's going to be this plus this. So that's going to be 1298.15 Kelvin. So that's what this is here, right? That's what that is there. So this will be 1298.15 Kelvin. Now, notice on the units here, the joules cancel, the Kelvin cancels, but the mole is still there. You just have to ignore that. That's unfortunately one of the things that happen with this type of problem. So we just ignore that. This then would give us a value. Now, I didn't do it this way. I'm going to show you a different solution, but we would plug this in. And so this would be E, E to the negative 72.812 times 10 to the third divided by 8.3145 and divided by 1298.15. So that would give us a K value of 0.001175. So at this point, we can compare Q versus K, right? So Q versus K. So according to what we've done so far, which direction is this reaction going to go in? Towards products or back towards reactants? Which way is this reaction going to go? Kaylee, what do you think?
Q will be greater than K.
Okay, so Q is greater than K. So what's that tell you?
It's going towards reactants.
Yeah, right. There's too many products, so back towards reactants. So back toward reactants. Now, let me show you another way we could have solved this. This is perfectly fine. If this is the way you choose to solve it, it's perfectly okay. There's another way we could have solved this though, right? We have another equation that says del G is equal to del G naught. In this case, because it's non-standard temperatures, we'll put that in, right? And then it was simply plus RT, the ln of Q. So we could have done it this way. I'm going to put this again in terms of our joules. Okay, so I'm going to go like this. So I'm going to put this in terms of our joules. So this is 72.812 times 10 to the third joules plus our R value, 8.3145 joules per Kelvin per mole. And again, we know that we're going to end up having to ignore that mole just like we did before. Our temperature was at 1298.15 Kelvin. Okay, and then the ln of Q, which I'm going to squeeze into here, the ln of Q, which we determined earlier, is being 1.166. And then I would plug that into my calculator. So I would take the 72.812 times 10 to the third. And now this is going to be joules, right? Because our Kelvins cancel. We're going to ignore this mole. This doesn't have a unit over here. So it's going to be plus 8.3145 times 1298.15 times the ln of our 1.166. And that gives us, now this is in joules, right? So del G then, del G would equal 74469 joules or 74.5 kilojoules. Now, if del G is this value, what does that tell you about the reaction? Which direction is it going to go in? Is this reaction spontaneous or non-spontaneous? Is this reaction spontaneous or non-spontaneous?
It's non-spontaneous.
Yeah, it's positive, right? Del G is positive, so this is non-spontaneous. So in chemistry, what does that mean? Which direction is this reaction going to go in?
To the reactants.
It's going to go back towards reactants. Remember, non-spontaneous means the reaction's going back towards reactants. So you could have solved this problem in either way that you wanted to, and you should come up with the same final result in the end. Any questions about that? Okay, let me do another one. This is one I actually wanted to do first. It's easier than that one. Okay. So this is number 48 from chapter 18. It says pure liquid nitric acid, so there it is, pure liquid nitric acid can be produced by reacting stoichiometric amounts of nitrogen dioxide with water. Now what it means by stoichiometric amounts is that we're going to have exactly the correct number of mounts according to the moles, so that when we're done, this should be completely gone and it would be all products. Except, of course, it's in equilibrium, so that's not going to happen. But the point is we don't want extra liquid in there, because that, of course, would react with nitric oxide to form aqueous nitric acid. We're trying to form just pure liquid nitric acid, really nasty stuff. Okay. So determine the equilibrium constant for this reaction at 175 degrees Celsius using the standard thermodynamic values. So again, we're looking for K. And again, we know that if we're looking for K, just like we've seen in the last problem, if we want to use the standard thermodynamic values, we know, of course, that del G is equal to negative RT, the ln of K. Okay? Except, of course, we're doing this at non-standard temperatures, so that's going to have to be del G of T. So then we would simply rearrange this equation, right, like we did before. And so this is just going to be E to the negative del G of T over RT. And this is a sub T right here. It doesn't really look like it, but that's sub T. Okay. So again, we're going to go through the same thing. We got to find del G. So we're going to do that. And whoops. And again, we're going to do that. But since it's at a non-standard temperature, just like we did before, we will need to use del H and del S. So we'll look up the free energies of formation in kilojoules per mole, and we'll look up the absolute entropies in joules per Kelvin per mole. And so again, we're just going to look these up in the table. And so it'll be 33.2 kilojoules per mole for the enthalpy of formation and 240.1 joules per Kelvin per mole for the absolute entropy. And then we'll just look up the rest of the values. And again, we're going to look up both of the values for each just to save time. And now we need the summation laws. So we have our 2 moles of liquid nitric acid at negative 174.1. Add to that to the 1 mole of nitric oxide at 91.3 kilojoules per mole. We'll subtract from that the reactants. So there's the 3 moles of the nitrogen dioxide at 33.2 kilojoules per mole. Add to that the 1 mole of water at negative 285.8 kilojoules per mole. Again, all the moles cancel. We have mixed operations. If you're following sig figs, it's not going to matter because 33 times 3 is going to be 99.6. So it's still going to be one pass. So they're all one passed. So even this one here, 2 times that, still going to keep it one passed. So your del H value then for this problem would have been negative 70.7 kilojoules. We're going to do the exact same thing for del S. So the 2 moles of liquid nitric acid. This time 155.6 joules per Kelvin per mole, plus the 1 mole of nitric oxide at 210.8 joules per Kelvin per mole. Subtract from that the 3 moles of nitrogen dioxide at 240.1 joules per Kelvin per mole, plus the 1 mole of water at 70 joules per Kelvin per mole. Again, all of the moles cancel. And you're going to get a value for del S then of negative 268.3 joules per Kelvin. Now, in this case, again, we know that we're going to end up having to use this. So R is going to be in joules per Kelvin per mole. So I'm going to convert this then to joules as well. So again, this will be negative 70.7 times 10 to the 3rd joules. And now we can plug this into del GT, which of course is del H minus T del S, which is going to be negative 70.7 times 10 to the 3rd joules minus the temperature. So the 175 plus 273.15 is equal to, so that's going to be 448.15 Kelvin. So 448.15 Kelvin times our del S, negative 268.3 joules per Kelvin. Our Kelvin cancel. We're going to have joules minus joules. It's actually going to be plus, right? Because we have minus minus. And so del G of T then is equal to 49.538 kilojoules. Okay, so it's positive. So del G of T is positive. So what does that tell you about the value of K? If this is positive, what's that tell you about the value of K? And again, you want to think about this stuff so that you can make sure that your work is correct. So what do you expect the value of K to be if del G is this value? Tell me what this tells you at all. What does this value tell you about this reaction?
It's going to be non-spontaneous.
Okay, and if a reaction is non-spontaneous, how does that relate to the value of K?
It means that it's going to go back to the reactants.
And what does that mean about the value of K? You're right. What does that mean about the value of K, though? And it's not going to go, I'm sorry, go ahead.
K is less than Q.
1, right?
Oh, 1.
When K equals 1, we have equal reactants and products. When K is less than 1, that means that the reactants are favored. And so that's all that means, right? So we know that K is going to be less than 1 because this is telling us it's non-spontaneous. It's non-spontaneous, and thus K must be less than 1. So we can confirm that, right? So K is equal to E, we're just plugging it in back into this equation here. So K is equal to e to the negative 49.538, and this is joules, right? I have kilojoules here, but this was joules minus joules, so that's joules. So this is times 10 to the third joules. And then we're going to divide that by our R. And our K value, which was 448.15 Kelvin. And again, this mole is going to magically disappear. Okay, and that would give us a value then of e to the negative 13.29, which would be 1.683 times 10 to the negative 6th. So basically then this is going to be 2 times 10 to the negative 6th. So as we expected, K was much less than 1. Okay, any questions about any of that good stuff?